professor since the last 15 years approximately at Gothenburg, but he started really from Breslau, Poland, Wrocław in German pronunciation, but that was in the 60s, namely in 68, and he's very proud of having been able to work and do his master degree at that university at exactly that time of the student revolutions, and we will be happy to tell you more about this at some other point, of course. But then he moved on, worked as a mathematician for a year, but then moved and decided to do his PhD in theoretical physics under the leadership of André Trautmann, and worked on rotation in GR, general relativity. After his PhD in 74, he moved to various places, including Stanford University, Austin, Texas, and then Oxford. And that is where he got in touch with Stein, with whom he has been interacting for a very long time until today, of course. And but because Dennis Schaumer moved to Trieste at some point, Marek moved with him. And so he stayed in Trieste for another 15 years, until eventually he decided to leave the south, go to the north, stayed some time at Nordita in Copenhagen in the early 90s, and then received his professorship in Sweden. Shortly after his arrival here in Sweden, he also made big impact in science, but also in the Swedish science press, because he was awarded the recognition of the most cited paper is between 1995 and 2000 in theoretical physics and experimental physics. So it's a great honor, therefore, for us to not only have Professor Marek Abramowicz with us here in Sweden, but moreover to have the opportunity to spend some time here at Nordita to run a mini workshop which is now running for 2 weeks. And as part of this, he will be giving the General Physics Colloquium to us today on the topic of observational constraints for primordial mini black holes. Marek, please.
Thank you very much, Axel, for this kind introduction. Many of you probably recognize the man on the photograph, who is Bogdan Paczyński, a great Polish astrophysicist, who died a few years ago. He was a professor at Princeton University for many years, and he was my very good friend and mentor for a long time, first in Poland and then at different places in the States. And I started with a photograph of him because this research, which I've done with a few colleagues recently, was inspired by his ideas. So the subject is observational constraints for primordial mini black holes. But before I will come to this subject, I would like to start with something else. And as Axel said, I came to Sweden in 1993, but my first encounter with Swedish science happened, in fact, much earlier. This on the picture here, you see Auditorium Marianum, which is a Baroque music chamber of my alma mater, University of Breslau. It is how it looks like today. But in 1945, the year I was born, photograph taken from the same place of the same music chamber is this one. It was after the war. It was burned down, like the whole university. That is my university in Breslau in 1945. Most of Polish universities in 1945 looked like this, and so our libraries. And then I come to the point of my first encounter with Sweden. That is a book on calculus, which was used still in early 60s when I was a student of this university. And there is a little note here in Polish which says, I will translate this to English, this book was printed in Sweden as a gift of Swedish government for rebuilding of Polish culture. And it was a very generous gift of Swedish government. There are many books, some all printed in Sweden, some in very well-known printing houses. It is one of the oldest in Sweden. And you may recognize some of the authors. Stefan Banach, very well known for his space and algebra, or Wacław Sierpiński of Sierpiński Quartet, and other things. So that is a great list of books, all printed in Sweden as a gift of Swedish government to rebuild Polish culture. And I would like to say, as a Pole, a Swedish professor now, but born as a Pole, thank you very much, Sweden, for this help. So I will be talking today about two issues. Dark matter in our galaxy and a possible way to detect mini black holes which may be or present in this dark matter halo. So let me first start with telling you what is the problem with dark matter in our galaxy. When we measure the rotational speed of stars which are moving in our galaxy around its center, and we plot the so measured orbital speeds versus distance, we are getting this rotational curve which are flat at a very large distance. It is not what theory predicts. When we calculate gravitational potential from visible matter, we do see matter in our galaxy, so we may calculate from what we see, distribution of matter and mass in our galaxy, the potential, and then calculate what would be the orbital motion. That's Newtonian theory, very well-known basic physics. All these curves, they are for four different galaxies. For our galaxy, it will be the same. These curves should go down in inverse proportion to the distance, to the square root of distance. But they do not. And one of the explanations, not the only one, but the explanation which we think astronomers and physicists is the correct one, is that there is a lot of matter in our galaxy and in other galaxies which we do not see. And this matter is called dark matter. And in fact, when we make a budget of matter in the whole universe, it is about 22% of matter in the whole universe which we do not see. And we do not know what is the nature of this matter. Then, of course, you know that there is, in addition, a cosmological problem with dark energy, that about 3/4 of all the stuff in the universe is in the form of dark energy, which is even more mysterious. But I'm not talking about dark energy today. I'm talking about dark matter, and dark matter in the halo of our galaxy. Let me, do you see this well? So let me only mention that by doing astronomical measurements, we know really a lot in a very detailed way about luminous matter distribution in our galaxy. So it is our immediate neighborhood, about 10 years 10 light years across. We do see some stars near Sun. Then when we increase the region by a factor of 10, then we do see brilliant stars, very luminous stars. Then another factor of 10, we do see the spiral structure of our galaxy. Then next factor of 10, our galaxy, and it is a small dwarf galaxy nearby. Then that is the local group, or rather the next one is the local group, our Milky Way, Andromeda, and a lot of dwarf galaxies. Then we see cluster structure and supercluster structure. And then when we go still one factor of 10 more, 1 billion light years, the universe is uniform. But we do see all this structure in our galaxy. that is, of course, microwave background radiation, which reflects of this uniform distribution on large scale in the universe. So, one of the questions in cosmology, in astrophysics and in physics, which is not solved in every detail, is how structures emerge from this uniform matter distribution in the early universe, and how to get from uniform distribution like this, all these structures which we do see. And as I said, we know a lot today about possible ways of these structures emerging, but we do not know yet all the details. And the second subject of my talk today, they are linked together, are hypothetical mini black holes. And I would like first to tell you only how small these black holes are. So I will be talking in my colloquium today about black holes in a particular mass range from about 10 to 15 grams to about 10 to 25 grams, for the reason which I explain later, why this particular range is interesting. So let me compare this to mass of Earth, which is 10 to 28 grams approximately, or mass of our Sun, which is 10 to 33 grams. So these black holes are very tiny objects, if they exist, in terms of mass. But they're extremely tiny in terms of their sizes, because there is one-to-one correspondence for black holes between mass and size. The size of a black hole is proportional to its mass. And for this 10 to 15 gram black hole, size would be 10 to minus 13 centimeters, about 1/3, which is about the size of the nucleus of helium. It's extremely tiny. It is really like an elementary particle, or even it's of the order of elementary particle. Let me make here a remark which is not connected to my talk. But when I told a colleague about my talk earlier today, he made a remark how one compares this to these hypothetical mini black holes which may be produced in CERN. Now we we all know this and we read this on newspapers. These are even much, much smaller. They are about 20 orders of magnitude smaller than the mini black holes of astrophysical interest I'm talking today. So I'm not talking about these super small black holes from CERN, perhaps. I'm talking about much larger, but still extremely small. I said that the size of a black hole is determined by its mass, and if we would have a black hole with a mass equal to the mass of Earth, the size would be 4 centimeters. Let me discuss a little bit the very concept of black hole, or rather these aspects of black hole physics which will be relevant for my talk. So then, of course, the modern history of black holes. History of black holes is a bit longer, but the modern history, the real understanding of black holes, of course, started with Albert Einstein and his idea that gravity should be understood as the curvature of space-time. That is a figure which, a cartoon which illustrates this in some way, taken from Encyclopedia Britannica. A cartoon representation. We cannot really make a good figure of the curvature of three-dimensional space or the space-time. So that is only to tell that gravity in Einstein's theory is connected to space-time curvature. But I will be really talking only about one particular aspect of the curvature, which in astrophysics we call very often compactness. And that is the ratio of mass to size. So the question is how much mass I'm putting into how large mass I'm putting into how small a volume. And that is the size of a black hole. The size is proportional to the mass. G is the gravitational constant, c is speed of light. That is also this formula known as, and I must now ask my colleague Kristen, who knows the difference between gravitational and Schwarzschild radius. I never know whether we call it Schwarzschild radius or gravitational radius. Please help me. Kristen, if you are here. Okay, I will call it gravitational radius. So that is gravitational radius of the black hole. And that is at the same time a minimal size which any object could have. Compactness for such an object, for a black hole, is 1. The greater the compactness, as it is illustrated here, the greater the curvature of space-time. Here, of course, it is a kind of an only representation. So, for the Sun, the corresponding black hole would have the size of 3 kilometers. Carl Schwarzschild and Roy Kerr, they found from Einstein's field equations the 2 solutions, exact solutions, which, if we take away cosmology, are probably the most important exact solution in Einstein relativity for astrophysics. Carl Schwarzschild, in the same year in which, in 19 15, in which Einstein published his field equations, solved them for a non-rotating black hole. So black hole solution, non-rotating black hole solution, exact solution was known right from the start of general relativity, and then much later Roy Kerr found a solution for a rotating black hole. Then there is also a solution for charged black hole of less importance for astrophysics because large astrophysical objects are uncharged. Black holes, it was a long sequence of getting the final proof. Black holes are characterized only by total mass, total angular momentum, and total charge. These are the only three characteristics of a black hole. So astrophysical black holes do have mass and angular momentum, and the solution was found by Roy Kerr. Now, if you have an object like a star, how could you make a black hole out of it? And nature knows two ways, basically, to increase compactness, to make a black hole from a given object. And it's obvious that if you squeeze an object, keeping its mass constant, so the compactness will grow, and this is the way by squeezing that you may produce a black hole. But compactness cube is mass squared times density. So if you have a lot of identical objects with the same density and you are collecting them, then you may also construct a black hole. And it's interesting perhaps to mention that it was this earliest ideas about black hole by John Mitchell and Marquis Laplace were based on collecting rather than squeezing. And we know that nature is using both ways to produce really existing black holes in our universe, by collapse of a star, and this way black holes with stellar masses are produced, or by merging many stars, and in this way we think supermassive black holes, which exist at centers of most galaxies, formed. And that is astronomers' way to measure compactness. So stars are often in binary systems, two stars orbiting each other. And when we observe light from such a system, the brightness, the luminosity, luminosity will, of course, because they are self-eclipsing, change this way. We also observed position of the spectral lines, and they are shifted because of the orbital motion. From this, we may directly measure radial velocity. From the shape of this curve, it's obvious that we may do it, but details are not important. We may know inclination. So knowing radial velocity and inclination, we know the orbital velocity. Then orbital psi is orbital period, which is of course directly measured times the velocity. And then from Kepler's law, mass is orbital size cube divided by orbital period squared. So that is a direct way of measuring masses. And astronomers know very well how to do it. Oops. There are some complications because in some binaries we also have, in addition to these stars, accretion disks, another source of light, but we also can handle this, and these are measurements. So in several binaries in our galaxy, these mass measurements have been done, and that is the result. Not all of them, but some representative measurements. So what I would like to show you here is that there is a line 1.4 solar masses, and around this line there are mass measurements, some of them very accurate. These most accurate measurements are from binary pulsars. Pulsars are like very accurate clocks orbiting each other, and therefore the mass may be, by the method I outlined, measured in extremely accurate way. And then there is also a line of about 10 solar masses, and you do see that you have like two populations. One with masses near 1.4 solar masses, and one with masses which are obviously greater than this mass. This 1.4 is a very important mass in astrophysics. It's called Chandrasekhar mass. Chandrasekhar realized that if you have a body which is made of degenerate gas, and you increase the mass, like in this cartoon on the right, then because of the gravity, the size of the body will decrease with increased mass. And there is a critical mass to which you can go. It is 1.4. If one would increase the mass above this limit, there will be dynamical collapse. So that is why these neutron stars have their masses not in excess of 1.4. And of course, black holes have masses greater than that. Not only we know the masses, but we know from direct measurements the size of these binaries and the size of accretion disk. It is a lot. It's a very standard, very well developed astrophysics. We do understand this object with black holes. Let me impress you by telling how small these binaries are. That is the distance from Sun to Mercury. So they are very compact objects. The black hole is always at the center of this accretion disk. So small that it would be even less than 1 pixel on this graph. So we do only see the companion star and the accretion disk around the black hole. And the black hole physics, the accretion disks around black hole physics is quite complicated. It is an example of hydrodynamical simulation which was done by Igor Igumenchev when he was with me in Göteborg. And I'm only showing this to say that it's a complicated physics, probably unrealistic, like several of my colleagues would say, because it is pure hydro with alpha viscosity. I'm sorry to say this. But nevertheless, what you may clearly see is development of convection. Beautiful, there are these there is no symmetry. There is no axial symmetry, there is no plane symmetry. They are non-stationary, they are generically non-symmetric, and that is what I do most of the time, and of course it is what Professor Brandenburg is doing here at Nordita, and many other people who attend the workshop which Axel Brandenburg mentioned. So that is the excitement. Now I'm going to this other class of black holes, supermassive black holes. This is not a simulation. This is a series of actual photographs which was made in infrared of the galaxy center, our galaxy center. We do see stars which are moving on orbits around invisible massive object in the very center of our galaxy, which is called Sagittarius A star. So from the measurement, that is Kepler's motion, from the measurement of these orbits, we of course can measure accurately, estimate accurately the mass of this object, which is in the very invisible mass, and I put here 3 millions. It's a little bit more, but we know this the mass of this black hole in a very accurate way. Okay, so we know, and it is not hypothetical. We know that for sure there are 2 classes of black holes. They are observed and they are very well understood by today in many respects. There are several others which we are still working on, but the very idea that there are real black holes which we observe and they behave the way we think they should, they are in 2 classes. Stellar mass black holes, which are called sometimes some of them microquasars, because they are scaled down version of quasars, these supermassive black holes with their accretion disks. So these are astrophysical black holes. We know that they are there, for sure. But when they ask the question, the theory, Einstein's theory as such, and then this particular exact solution by Schwarzschild and Kerr do not show any mass scale. A black hole, according to theory, Einstein gravity, could be of any mass. So the question is, why there are only these 2 rather narrow mass ranges? And in this transparency, I'm saying that although black hole theory does not give any mass scale, the real universe, of course, does. And let me start from something which is very interesting by itself, and that is Hawking radiation. So, I already told you that the typical size, the size of the black hole is proportional to the mass and equal 2 times gravitational constant mass divided by c squared. That is called, that we call gravitational radius, which here is denoted by Rg. So if one would say, what is a typical frequency which you think should occur for all kind of oscillations in strong gravity near a black hole, you divide velocity of light by this size of a black hole, you have the frequency. So it is, the frequency is inversely proportional to mass. And it's interesting that we do observe such frequencies as so-called QPOs. That's one of the reasons of our conference. But then you may say, the energy, if you have frequency, this frequency, then energy would be Planck constant times this frequency, but then you may say, if it is kind of something thermal, it would be Boltzmann constant times temperature. And from
from this two, from this equality, and then from the fact that you already calculated this gravitational frequency, you may calculate the temperature. And that is the temperature of the Hawking radiation with accuracy to some numerical factor. So that of course, not this order of magnitude estimate, but a semi-classical treatment of gravity led Hawking to suggest that black holes have really this temperature, and they therefore radiate radiation, Hawking radiation. This Hawking radiation is like black body radiation, so flux is proportional to the force power of temperature, and therefore inversely proportional to mass in the force power. But then the power of radiation, luminosity, is the flux times area, but area is Rg squared, and both of these quantities depend only on mass, so the power is 1 over mass squared. But then you may say that when power is emitted, that is because the energy of black hole, which is mc squared, is changing. From this, it's easy to see that the time scale for total evaporation of a black hole due to Hawking radiation is proportional to the mass cube. And if I would put this constant of proportionality, which you have them all above this line, then I would be able to say that if this time is equal to the Hubble time, how old the universe is, the mass is equal to 10 to 15 grams. So that is why it is an interesting mass for a black hole. If there would be a black hole created at the beginning of the time, at the Big Bang, or soon after Big Bang, it will evaporate totally today. So we do not think that there should be smaller black holes around than 10 to 15 grams. That is the lower end of the mass spectrum of the black hole. Now I must wait. That is and the idea about primordial black holes was with us from really late 60s. The same authors, Russian authors, published in Russian a paper in late 60s, and that was the first version published in English. It's a very well-known paper, which and there are independently other authors were studying approximately the same time the same problem of formation of primordial black holes in the very early universe. I will not go into details. We know, for example, from many of these papers, what people think the so-called initial mass spectrum of these primordial black holes should be. So how many of them are small in mass and how many of them are large in mass. That was calculated. But my point is this. Even if I know this initial mass spectrum, even if I would say, okay, we know the physics of the early universe so accurately that we can calculate this initial mass spectrum, I'm not interested really in this. I'm interested in black holes in the dark halo of our galaxy. And this mass spectrum at the early universe may be very much different than the mass spectrum in the halo or mass spectrum of black holes, if they are there. Because the formation process is a very complicated one, and we do not understand it. dark energy and dark matter are certainly involved, etc. So we do not know really. There are no good theoretical ways of predicting what is the mass spectrum of these black holes. For this, we must ask experiment. And the question is, are there observational constraints to constrain the mass spectrum of black holes, of possible black holes in the dark halo of our galaxy? And people consider seriously two such constraints. One based on gravitational microlensing, and one based on Hawking radiation. If there are tiny black holes, they will evaporate, and we may detect flashes of gamma rays, which were not detected. And if a black hole is passing the line of sight, it will act as a gravitational lens, will record the event, and then we may have a detection. So these two methods have been used, and that is a figure which in our paper we prepared. There are constraints from microlensing and from Hawking radiation. So Hawking radiation constraints are pretty strong. The share of these hypothetical primordial black holes of mass of around 10 to 15 grams must be really very small. So small that, I think to some theorists it is embarrassing. There are no such black holes. And from microlensing, there are constraints, not so acute, so there could be. But of course, in microlensing, they are unable to distinguish between black holes and possibly other objects. So that is a very, very upper limit. But that is not the point. The point is that there is a huge mass range from 10 to 15 to 10 to 25 grams, which is unconstrained at present. We have no information, either theoretical or from experiment, to tell anything about possible black holes in this mass range. So, the idea, our idea, was this. Suppose that there are these black holes in this mass range, in dark halo. They will be colliding with stars, or possibly even with Earth. Could we see signatures of such collisions? That was the subject of our research. And I am starting about our research so late in my talk because the answer is we were unable to find any potentially observable signature of ours. So I already answered the question. These are ideas which then we calculated a little bit more accurately in the paper. So there are two issues. How often a collision would happen, and what is the energetics of the collision? Okay? How often and how powerful in energy? These are the two questions one should ask. So the probability, the probability to know the probability of the collision, you must calculate the cross section for the collision. And this cross section is not a complicated thing. It is either a direct hit, or it is that a bigger body can gravitationally capture a black hole. So then we know the cross section, but it is obvious that this probability is higher when we have a higher number of these hypothetical black holes in the dark halo. But because the mass of the halo is fixed, we know the mass of the halo, so the smaller black hole, the more of them we have, and therefore the probability goes up in inverse proportion to the mass of this hypothetical black hole. Okay? The smaller the mass, the higher the probability of the collision. But then the problem is that then energetics of the collision, of course, goes the opposite way. So the more massive black holes would produce on impact stronger signals, more powerful signals. So we have two opposing factors. We would like to have this black hole, this hypothetical black hole, very small in order to have high probability of a collision, but at the same time we like these black holes to be massive enough in order to produce a signal which we can detect. Okay. And then when you have two opposing trends, then there would be a minimum, which is the best we can do. So what we calculated in this paper, we took several instruments which astronomers have. For example, this gamma ray satellite. And for different targets, like main sequence stars, red giant cores, white dwarfs, and neutron stars, we calculated these two opposing trends, and these minima, as I said, correspond to the best case we can have. The embarrassing fact connected to this plot is that on the vertical axis, we plotted the time of how long should you wait with this instrument to see one photon from all the targets in our galaxy. And the best number for this particular instrument is 140 years. 140 years, you will get one photon from collision of a hypothetical black hole, which would then have mass of about 10 to 25 grams, from all main sequence stars in our galaxy. So the obvious thing is that is undoable. And that is the result, very negative result of this research we have done, and we the names are here. Julia Becker, she's a postdoc at Göteborg University, got her PhD at Düsseldorf University recently. And let me mention another member who is here now in Stockholm, Fredrik Johansson, who is a PhD student at fundamental physics at Chalmers University. So, very negative result. One must, but that's good in a sense, that if there are signatures of such collisions, then one must go to some more sophisticated idea than just to get photons out of the collision. And I've mentioned Bogdan Paczyński. His idea was not that one can observe directly these photons out of the collision, but that black holes are kind of a catalyst, that there is a large reservoir of energy. But of course one then must find this reservoir in a star, and black hole strikes and release this energy. So this energy is much larger than the energy of the impact. But nobody knows what this reservoir could be. Okay, thank you.
Thank you, Mark. For this very interesting lecture and sharing with us some of your recent work.
be to produce black holes in this mass range?
The several mechanisms were suggested. The most often people think of collapse of overdense regions. So we know that although universe is very uniform, it cannot be totally uniform because other structures will not be formed, like galaxies and stars and cluster of galaxies, etc. So we know that there are density perturbations, and in this very paper by Novikov and colleagues, which I showed, this is the mechanism, that it is a direct collapse of an overdense region of the universe. But there were other mechanisms suggested as well. So if it is a direct collapse, then it would be like that in these mechanisms, small black holes are produced much more often than large black holes.
Any other questions? Please.
Can you explain what would happen when a small black hole hits a rock, for instance? What would happen? Would it look like shock? Or I can imagine the black hole would absorb some of the matter in the rock.
Yes, many people think like this, but these black holes are very tiny, and therefore, if you kind of could imagine that you are this black hole zooming at Earth, then you will see atoms very far away. This black hole is just see Earth as a vacuum, really, and direct hits black hole and atoms in Earth are very rare. The interaction really is gravitational. That these atoms are attracted by black holes, may collide, form a shock, and energy is dissipated in this shock. But that is a very inefficient way of transforming kinetic energy of a black hole into heat by this gravitational drag force. And if we would have an impact of 10 to 15 gram black hole on Earth, this 10 to 15 gram black hole will go through Earth like knife through butter. There would be no effect. If it would be, however, a planetoid of the same mass, that it would be disaster on planetary scale. So black holes, because they are so tiny, they are not dangerous. That is the problem of detecting them, that they are not doing much on a collision.
Many stars occur in binaries. Could these black holes also occur in binaries, and you could actually see them through the Doppler motion of the companion star, if that is one? It's a visible planet in that case.
But it would be very difficult to see how such a tiny black hole could be captured by a binary.
Yeah, but if it's formed.
Yes.
It's formed like this, as I said, many
So,
stars are binaries.
one of the idea which people suggested is that these mini black holes can influence the motion of asteroids in our solar system, and by doing very sophisticated statistical analysis of motion of asteroids in our solar system, we may put some upper limits of the existence of these black holes. Axel, I have another transparency, not connected to black holes, connected to, indeed, Oscar Klein. We are in the room which is dedicated to the memory of Oscar Klein. And that is something which will take 1 minute, if you allow me
You
to.
have to do that if it's
Okay. No, but then I don't know whether you will be pleased with what I do. Okay. Then, when I knew that I will give a lecture in this lecture hall dedicated to the memory of Klein, I thought perhaps it is the Klein from the Klein bottle. But of course he is not. He's the Kaluza Klein. And the Klein bottle Klein was Felix Klein, older than Oscar Klein. To his memory is dedicated this room. And that is this kind of mixing up Kleins happens all the time. And that is really my story. Some time ago, long time ago, at the beginning of the previous century, when Albert Einstein was young, there were 3 famous Stein. Gertrude Stein, who is a very influential writer, Sir Jacob Epstein, who was a sculptor, also very influential, and Albert Einstein himself. And they were so famous that their fame bothered people, and somebody wrote a limerick. What a wonderful family is Stein. There is Gert, there is Ep, there is Ein. Gert's writings are bunk, Ep's statues are junk, and nobody understands Ein.